All right, good morning, Omaha. I'm Dave Aronson, the T-Rex of Codosaurus, and I'm here to teach you to kill mutants. But before we get started with that, I think we need to level set some expectations. First, to call this an advanced talk might be a tiny bit misleading, but to call it an introductory talk would be even more misleading. What this is an introduction to an advanced topic. So if you're already well-versed in mutation testing, I won't be too offended if you go seek better learning opportunities at another talk. But I'd still rather you stick around so you can correct my mistakes later in private. And I mention mistakes because I'm not an expert on mutation testing. One of the dirty little secrets of public speaking, including at conferences, is that you don't really have to be an expert on your topic. You just have to know a little bit more than the audience and be able to convey it to them. And mutation testing is so rare that most developers haven't even heard of it, so it's a great subject for this. So let's start with the basics. What on infinite earths is mutation testing? In our world, that of software development, not comic books, it is, surprise, surprise, a software testing technique. Now you might look at the name and think, well, obviously it's about testing the mutations used in genetic algorithms. But no. It's about testing our test suite and our code by using mutations. Its obvious benefit is to ensure that our tests are strict by finding the gaps in our unit test suite. Once we've found those gaps, we can improve our tests and close up the gaps. Lack of strictness comes mainly from lack of tests, of course, poorly written tests, and tests that are not well maintained, that don't keep pace with changes in code. But speaking of our code, mutation testing can also help ensure that our code is meaningful, by which I mean that any small change to it has a noticeable effect on its behavior. Lack of meaning comes mainly from code being unreachable or redundant or otherwise without any real effect. Once we find meaningless code, we can just chop it out. That's pretty easy. Mutation testing puts these two factors together by first ensuring that some tiny little change to the code has a noticeable effect, and then that our tests do notice that change and fail. Now, not all the tests have to fail, but every change should make at least one test fail. Of course, this implies that our test suite passes with our original untouched code so that we can tell the difference. Mutation testing does all this by mutating our code, hence the name. But don't worry, our code is sitting safely on disk, untouched. These tools, at least the ones that have gotten any successful traction, use copies of our code, usually in memory. It mutates these with the intention of creating test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And because of this, it's sort of related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix discover flaws in their error recovery process, mutation testing helps us discover flaws in our test suite and our code. But the way mutation testing works is sort of upside down from what Chaos Monkey does. Chaos Monkey is known for a lot of things, but primarily for injecting faults, such as dropped connections, into Netflix's production network. Mutation testing, however, injects semantic changes. It doesn't know whether these changes are going to produce faults or not, though we hope they certainly will, but that's up to the test suite. It injects them into copies of our code, not our actual network. It does its work in our test environment, not production. And if everything still goes well in the sense that our unit tests all pass, that does not mean that everything is okay. That means that there is a problem. Remember, every change should make at least one test fail. If that happens, then we know that everything's fine. In the sense that our code is meaningful and our tests are straight. But there are some drawbacks, so it's really no silver bullet. Besides, we developers know there's no such thing. Plus, those are for killing werewolves, not mutants. Any resemblance to Tech Squatch is purely coincidental. No monsters were harmed in the making of this presentation. The first drawback is that it's rather hard labor on the CPU. So it's usually rather slow. We certainly won't want to mutation test our entire code base on every save. A more realistic scenario might be overnight for a fairly small system, or maybe over the weekend for a larger one. Fortunately, most of the tools include an incremental mode, so that we can test just what was changed since the last time we mutation tested. That we might be able to do on every save for a rather small system, or at least over a shorter break for a larger one. Its CPU-intensive nature can also run up our bills on cloud systems such as AWS or Azure or whatever. Another drawback is that mutation testing is not at all a beginner-friendly technique. It only tells us that making some particular change to the code did not make any change to the test suite, or any difference that the test suite could tell. But what does that even mean? It takes a lot of interpretation to figure out what a mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but they have a much larger vocabulary, so they're not always just on about brains. Even worse, sometimes it's a false alarm, and the mutant didn't really make any difference in the first place, at least that we care about. But it can still take a lot of time and effort to figure that out. And even aside from all of that, there's frequently a lot of code that we shouldn't bother testing in the first place. Suppose we have a debugging log message that says, the value of x is, and then the value of x. That constant part, the value of x is going to get mutated, even though we don't really care about it. Fortunately, most of the tools do include some way to use comments or other such configuration to tell it to ignore a given line or perhaps even a whole function. But those comments can usually clutter up the code and make it a little less readable. Now that we've taken a look at some of the major pros and cons of mutation testing, what exactly does it really do and how? Let's peel back one layer of the onion and look at it from a high-level view. First, our tool will break our code apart into pieces to test. Usually these are our functions, or methods if we're using an object-oriented language, but I'm just going to say functions. Then it tries to find the tests for each particular function in turn. If it can't find any tests for the given function, some of the tools will use the entire unit test suite, which is horribly inefficient and leads to even more false alarms. Fortunately, most of them will just skip that function, and even better yet, most of those will warn us, so we know we should go do something about that, like write some tests for it, or at least annotate some tests that already exist, but more on that later. Assuming we're not skipping this particular function because of lack of tests or whatever reason, the next step is for the tool to make the mutants. To do that, it looks closely at the function in question to see how it can be changed. And for each tiny little way that function can be changed, the tool will make one mutant with that particular change. And once it's done making all the mutants it can from that one function, it will iterate over the list. And now we get to the heart of the concept. For each of the mutants derived from one particular function, the tool will run that function's unit tests, but using each mutant in turn instead of the original function. When each mutant encounters one unit test that fails, that's called killing the mutant, and it's a good thing. It's exactly what we want. It means that the tiny little change that the tool made to create the mutant had a noticeable effect on the behavior, and the tests were strict enough to notice that change and fail. At this point, the tool will stop running any more of the unit tests against that mutant and go on to the next one. Or if it was the last one for that function, go on to the next function. Or if that was the last function, then we're done. After it's made one unit test fail, we don't care how many more it might make fail. Like so much else in computer science, we only care about ones and zeros. On the other claw, if it survives all the original function's unit tests, in other words, passes them, lets them still pass, then it has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out exactly how, and if need be, fix it. Now let's peel back another layer of the onion and look at some of the technical details of how a mutation testing tool will actually do this. First, our tool parses our code, usually into an abstract syntax tree, or AST. I know these boxes are a little small to read, but we don't need to understand this AST in detail. Some work a little differently, like operating on bytecode. Some of them, usually small proof of concept toys and whatnot, operate directly on the source code as strings, but most of them use an AST, so we'll just roll with that approach. After our tool creates an AST, it will traverse the tree looking for subtrees, or branches, if you will, that represent our functions. After finding them, it handles them more or less as I described before, looking for each one's tests. But how does it do that? That usually relies mainly on us developers annotating our code to our tests to say what function each one is for, or possibly following some kind of naming convention so it can just decode them. This is often supplemented and sometimes even totally replaced by the tool looking at what functions the test will call. Though this can get a little tricky if the function is not called directly from within the test. After the tool has found the tests for a given function, then, assuming it won't skip this function for lack of tests for whatever reason, it makes the mutants. So how does it do that exactly? To make mutants from the piece of AST, the subtree that represents a given function, it traverses that subtree just like it did the whole thing. Except this time, it's not looking for even smaller subtrees it can extract, but it's looking for nodes where it can change something. And for every time it finds one of those, it will make a fresh copy of the entire subtree that represents that function with that node changed in that way, or in each of those ways. For instance, suppose that AST that I showed before was traversed down to this not equal comparison. For each way it could change that one node, it would make a new copy of this entire subtree with that one node mutated in each of the ways it could change that. After it's done making as many mutants as it can from that node, it'll continue traversing the tree, most likely winding up at that node's first operand. And again, for every way it could change that node, it would make a copy of this entire tree with only that node changed in each of those ways. And so on until it has traversed the entire tree. So what kind of changes are we talking about? There are quite a lot. It could change a mathematical operator or a logical operator or a bitwise operator to another one. If the language allows, we can even change among those sets. It could change the order of operands in cases where it matters. It can change a comparison from one to another. It could change a logical or bitwise operator from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It could change a constant or variable or expression or function call to some other value. It could even change it to something of an entirely different and even incompatible type, such as changing a number to a, if I may quote Smeagol, string or nothing. It could even remove entire lines of code. It can remove a condition so that something that is normally either skipped over or done is always done. It can remove a loop control so that something that might be done once, skipped over, or done many times is always done exactly once. It can scramble or truncate the argument lists of function calls or of function declarations. It could replace a function's entire contents with a constant, or returning either of the arguments, or deliberately raising an error, or if the language permits, replace it with nothing at all. There are many, many more, but I trust you get the general idea. From there on, in the process of mutation testing, there aren't any additional low-level details I want to add. But to refresh your memory, the tool then tries to kill each of the mutants by running each of the original function's unit tests in turn until either one of them fails or it survives, that is, the mutant survives all of the unit tests, in which case it is reported as a surviving mutant so that we know we should do something about it. So now let's finally walk through some examples. And we'll start with an easy one. Suppose we have a function like so. I assume that's big enough font for you to see in the back of the room. Now I want you to think about what could a mutation testing tool make out of that. In particular, what would the mutants return? Because that's what our unit tests are probably going to be looking at. Mostly, it could produce mutants that return all kinds of values such as these. There are lots more, but I had to stop somewhere. Now suppose we had only one test, like so. This is a rather bad test, but even so, the vast majority of the mutants on that previous screen would get killed. The ones shown here in crossed out green. The ones returning constants are almost certainly not going to match because 4 is not a very common value to use in these sorts of things. The ones raising an error condition will at least make the tests not pass. Subtracting 2 from 2 gets us 0, dividing 2 by 2 gets us 1, returning either argument alone gets us 2. In any case, still not 4. But addition, multiplication, and exponentiation in the reverse order will also get us the correct answer, and therefore will survive that unit test, which, as you may recall, is our one and only test so far, so it will survive our whole unit test suite. Now, when we actually run the report, it should give us a report, when we run the tool, it should give us a report that will boil down to something like this, at least in a fairly terse mode. The exact wording and amount of context and symbols and whatnot will vary enormously depending exactly which tool we're using. But the information should be more or less the same. To unpack that a bit, first the minus and plus symbols mean that a line is removed or added, so the two of them together with the same line number just means there's a change. You've probably seen this sort of notation in a diff tool or something like that. To go into detail on the individual lines, it's saying that if we mutate the function called power, which is in file demo.p at line 42, and yes, P stands for pseudocode, don't bother trying to figure out what language this is. And if we modified it in any of 4 particular ways, then it would still survive our entire unit test suite. And it goes on to say that those 4 ways are, firstly, to modify line 42 to swap the arguments, or to change line 43 to change the exponentiation to addition or multiplication, or to change line 43 to swap the operands. So, what is this set of surviving mutants trying to tell us? The first step to figuring that out is to ask ourselves, how are these mutants surviving? Are they begging on the streets? Are they robbing banks? Are they living at the Xavier Institute? Oh, whoops, sorry, wrong mutants. The obvious answer for our kind of mutants is that they return the same value or have the same side effect as the original function, whatever it is, the return value, side effect, or whatever that the unit tests are looking at. To determine how that happens, the obvious approach anyway is to just take a look at the mutants, ideally in conjunction with at least one of the tests that they pass. So let's do that with the plus mutant. And looking at the change together with the test makes it a lot clearer that this particular one is surviving because 2 to the second power gives us the same number as 2 plus 2. And as we all know, that's 4, as the test also states. So how can we kill this mutant? In this case, it's actually quite simple. We just need to use a set of inputs to power such that x to the y is not the same number as x plus y. We could add a test or just change the one we have, such as asserting that 2 to the 4th power is 16. All the mutants that our original test killed, this would also still kill. But since 2 plus 4 is 6, not 16, this would kill the plus mutant. We also know that 2 times 4 is 8, also not 16. So it would also kill the times mutant. Yay! So let's rerun our tool and look at the report. And we see that we have indeed killed both the plus mutant and the times mutant. But both of the argument swapping mutants are still with us. How is this happening? Well, because of the way powers work, 2 to the 4th is the same as 4 to the 2. So since this function deals with powers, it probably would have been a little smarter not to use a set of inputs such that one was a power of the other. So let's just dial it back a little bit and change our test like so. Now we could have also done 2 to the 5th, 3 squared, 3 to the 5th, vice versa, and on and on. There are lots of ways to skin this flirkin. And this would kill the swapping mutants. We might be a little worried, oh, would that possibly revive the times or plus mutants if we just change this test rather than adding it to the one we had before? Well, no, it wouldn't, because 2 plus 3 is 5, 2 times 3 is 6. Both of those are not 8. So we've killed all the mutants, yay! So now the correct operation of exponentiation of This to that power is the only operation, or at least the only simple common operation likely to appear as a mutant that will give us the correct answer. Now this may make mutation testing sound simple, but remember, this was a downright trivial example, so that we could easily figure out a new set of inputs to make the mutant return, make all the mutants, all the reasonably likely mutants, return a different answer from the original function. So let's look at a more complicated example. Suppose we have a function to send a message, like so. And that is the main thing that I was worried might not be easily readable from the back. The gist of it is that this function, sendMessage, uses a loop containing send bytes to send as much as send bytes can handle in one chunk, over and over, picking up where it left off last time until the message is completely sent. Now, a mutation testing tool could make all kinds of mutants from this, but one of particular interest would be this. Again, the minus signs mean that a line is removed. So this is an example of removing a loop control, so that something that might normally be done once, done many times, or completely skipped, is always done exactly once. In other words, it's equivalent to this, which is the original function with the looping removed. Now suppose that this mutant survives our test suite, which consists mainly of this. There's a little bit more to it that I'm not going to show you quite yet. What does the survival of the non-looping mutant tell us? If a mutant that only goes through the while loop once acts the same as our normal code, as far as our tests can tell, then our tests are only making that code go through the loop body once. So what does that mean? You'll find that interpreting what a mutant is trying to tell you involves a lot of asking, so what does that mean? It's kind of like the 5 whys. Going one layer deeper, it means that we're not testing sending a message larger than send bytes can handle in one chunk. And again, this could be from several different causes, but the obvious one is that we just didn't test with a big enough message. For instance, here we have our maximum chunk size declared at 10,000 bytes. And yet we're only sending a tiny little 3-byte message. So how can we fix that? Well, the obvious answer is use a bigger message. And how do we do that? Well, fortunately, I've made the setup for that pretty simple. We just grab that chunk size declared in the network module, add 1, and make that bigger message, assuming, of course, that this is a public declaration so that we can use it down in our test. So that would be an example of when the problem arises from something lacking in the tests. But perhaps, to paraphrase Shakespeare, the fault, dear Omaha, is not in our tests, but in our code, that these mutants are survivors. Perhaps we did test with the largest permissible message, or at least message size, out of a predefined set. For instance, here we have small, medium, and large sizes, and we did test with a large. And yet this mutant survives. What is that telling us now? It's slightly different than what it told us when we were only testing with a 3-byte message. It's trying to tell us now that a version with the looping removed will do just fine, because that's exactly what the mutant is. If we also remove all the other stuff that we only need to support the looping, then send message boils down to this. And now it's really clear that the entire send message function may well be redundant. We could possibly just use send bytes directly. Now, I say may well be redundant rather than is redundant because in real-world code there may be additional things we need in send message, such as logging and error recovery and so forth. But at the very least, the looping was redundant. Fortunately, when it's this kind of problem with unreachable or redundant or otherwise meaningless code, the solution is usually pretty clear. Just chop out the extra junk that the mutant doesn't have, and then maybe go a step further and remove anything that is now not needed. And this will make your code cleaner, tighter, more meaningful, and more maintainable by getting rid of useless cruft. Now that we've seen a few examples of spotting bad tests and redundant code, I want to address a few frequently asked questions. First, this all sounds pretty crazy, deliberately failing tests to prove that the code succeeds. Where did this whole bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 as part of Richard Lipton's term paper titled Fault Diagnosis of Computer Programs. But the first tool didn't even appear until 9 years after that, in 1980 as part of Timothy Budd's PhD work at Yale University. Even after that, it still wasn't practical for most of us using consumer-grade or maybe workstation-grade computers as opposed to souped-up servers, mainframes, or gaming rigs. Until maybe the past decade or two, with the advances in CPU speed, multi-core CPUs, larger memory, and so forth. But that leads us to the next question. Why is it so CPU intensive? To answer that, we need to crunch a few numbers, but don't worry, it's pretty easy. Suppose we have a program made up of functions with about 10 lines each on average. And on each line there are about 5 places where it could be changed or mutated to about 20 different alternatives. That works out to 1,000 mutants per function. And for each one of those, we're still going to have to run probably at least a few unit tests, somewhere between 1 if we get real lucky and kill it on the first shot, up to all of the ones for that function if we get so unlucky as to kill it on the last shot, or worse yet, it survives them all. But suppose we wind up running even just 10% of all the mutants for a given function. Since we're starting with 1,000, that's still 100 times as many test runs as for our entire unit test suite. If we assume that our test suite normally takes a zippy 10 seconds, then mutation testing will probably roughly take somewhere around 1,000 seconds, given these numbers we're assuming. Now that might not sound like much, but divide by 60 and you'll find that's almost 17 minutes. I don't want to sit around and wait for that, certainly not on every change. But there is some good news. Whoops, I think I forgot to advance a slide. There we go, there is some good news. Over the past decade or so, there has been a lot of research into trimming down the number of mutants, mainly by weeding out those that are semantically equivalent to the original code or redundant with another mutant, or trivial in some other way, like if it raises an obvious error condition that the original code is not going to catch. Techniques like this have trimmed the mutant horde down to about 1/3 under some cases. But even with that rare level of success, it's still no silver bullet, because this takes significant CPU time itself, and the rest of the mutants are still quite a lot. Oh, I think I must have gone the wrong way. There we go. It's no silver bullet. There we go. The last common question is, when making each of the mutants, why do we change them in only one way? There are a few different answers. First, it helps us poor humans focus. It's much easier to tell what a mutant's trying to say if we're only talking about one thing in the first place. You can think of it like using the single responsibility principle. Another reason is that multiple changes may balance each other out. That would lead to many more false alarms. For instance, remember that original very simple function and its argument swapping mutants? If one mutant had both of these mutations, then the first one would swap the arguments, and the second one would swap them right back, having no net effect and therefore guaranteeing that it would pass whatever unit tests you care to throw at it. Lastly, allowing multiple mutations per mutant would create a combinatorial explosion of mutants, with the tool making many, many times more mutants per function, which would make it even more CPU intensive. I'll spare you the math, but with one we have, as you may recall, about 1,000 with the assumptions we were making. If we allowed two, we would have almost 1 million, and with three we'd have almost 1 billion, and so on, multiplying by almost another 1,000 for each mutation we allowed further. Even if we weeded it down to about 1/3 at each step, with one we'd have 333, and 1/3, but I'm rounding. It'd be rather difficult to have a partial mutant. With two, we'd have almost 110,000, and with three, we'd still have over 35 million. But we can spare ourselves the huge workload of just creating the mutants, never mind running the tests, and the extra false alarms, and the lack of focus if we just limit it to one mutation per mutant. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's fairly easy to get started with in terms of setting up most of the tools and even annotating the tests. Yes, it may be tedious, but at least it's easy. However, it's not so easy to interpret the results of the tools when they report to us, nor is it easy on the CPU. Even if these drawbacks mean it's not necessarily a good fit for our current projects, though, I think it's still just a really cool idea in a geeky sort of way. If you'd like to try mutation testing for yourself, here's a list of some of the common tools for common languages and platforms, and some other ones. I doubt many of you are doing Fortran 77 these days. I'll pause a moment for you to take pictures. Just be aware that many of these might be outdated. I don't know or follow quite all of those languages. Moving on in a few seconds. Get your pictures in fast. All right, before we get to Q&A, I want to give a shout out to TopTal, a consulting network I'm in with a very strong community, including a speakers network that helps me prepare and practice this presentation. Please use this referral link if you want to hire us or join us. And also many thanks to Marcus Scherp, who not only created Mutant, the main mutation testing tool I've actually used, but was also very willing to answer my questions and even, again, critique this presentation, this time mostly for the factual content. And now it's your turn. I'll try to answer your questions, but remember my disclaimer at the beginning. If you think of something later, I'll be around for the rest of the conference, and if you think of something even more later, there's my contact information, and of course I have business cards. So, any questions? Okay, I don't see any hands raised. Okay, question.
Yeah, for languages that compile, especially that allow to compile, how feasible is this to create, compile 1,000 readings of an application, especially a large application, in any kind of realistic time?
Okay, the question is for languages that are compiled rather than interpreted or sent to bytecode or whatever. How feasible is it to actually run the mutation testing, especially the ones that take a while to compile, especially for a large system? In order to run the mutation testing and create the mutants, it doesn't necessarily have to compile immediately. I would say that does probably add quite a bit to the time to compile the mutants if that would need to be done. So yeah, I would say that that would take significantly longer than, say, for Ruby or Python or something. And again, those are slower in the first place than something compiled like C. So it's all a trade-off, I guess, in the case of a compiled language using a larger system. That would just be all more reason that the process could be slow, even though it's not necessarily a matter of just constructing the mutants. Great point. I think I will possibly add that to a future longer version of this presentation. Next question back there.
I kind of follow up on that. So it kind of focuses on one thing at a time, obviously to avoid any humans interacting with each other. Is it possible to avoid, at least cut down the compiling problem, have it do mutations on two separate functions at the same time, and it's obviously going to be confirmed that there's no crossover?
The gist of the question seems to be, could it be possible to cut down on the time it takes by separating things out and working on multiple different mutations, possibly different functions at the same time? And yes, many of these tools do actually try to parallelize things when possible. For instance, Mutant will let you say how many jobs to have at once simultaneously. At least on my poor old little Mac Mini, the fan gets rather loud if you set it to the number of cores you have, but I've found it's a good compromise to do about half the number of cores. Could also get a little fancier and try and have it do some compilation. If you're using a compiled language, wait for that I/O to finish while you devote the CPU to other things. I'm sure there's all kinds of ways we can increase parallelization and other tricks to pipeline it. Anything more? All right, we have about a minute left.